Hi, this is Barrett Givens, and in this video, we're going to do an example of a quotient topology using the idea of a gluing diagram. All right, so we're going to start off with this quotient space, and we're going to be given it using an equivalence relation. So we'll let x be I cross I. Remember, I is the unit interval, so this is 0, 1 cross 0, 1, so this is a unit square with an equivalence relation that says points 0y and 1 comma y are equivalent for any y value between 0 and 1. So 0y is equivalent to 1 comma y. All right, let's make a diagram to kind of illustrate what this means. So here's a picture of x. X is 0, 1 cross 0, 1. So it's a unit square. And then points 0y and 1y, those are points on the vertical sides. Okay, when x is 0, that's the left-hand side. When x equals 1, that's the right-hand side. And the points, like the two corner top points are equivalent, and then the points at like 3/4 on either side are equivalent, and then the points at 1/2 are equivalent, and 1/4. So basically, all up and down each side, there's these pairs of corresponding points. Okay? So like this point is equivalent to this point, and this point is equivalent to this point, and so on. All right. So what we want to do is we want to imagine gluing those points together. So I want to imagine taking this side and gluing it to this side. If we think of this as like a piece of paper that we could roll up and glue them together, what would we get? Well, I claim that we would get a cylinder. Okay, we would get a cylinder. And so the two corner points, 0, 1, and 1, 1, would be this point on the top part of the cylinder. And then the two bottom points would be this point on the bottom of the cylinder. This whole vertical line, which is equivalent to this whole vertical line, would become this single vertical line in the cylinder. Now, you might sort of wonder, well, can we do that? Like up until now, we've been talking about quotient topologies with a function. We can actually define a function. Let's go ahead and try to do that. So what I want to do is I want to take a function that inputs an x and y and outputs a point in R3 that would parametrize a cylinder. And I want the vertical lines here, these vertical lines should sort of correspond to going up and down my cylinder, and horizontal lines should correspond to going around my cylinder. So what I will do is I will say rho of xy, whoops, that was interesting. Okay, rho of xy will give me, I'll say it's cosine 2 pi x, sine 2 pi x, and then I'll use y as the third coordinate. So first of all, you can check. If you plug in rho of 0y, you get 1, 0, y. And if you plug in rho of 1y, you also get 1, 0, y. And so this surjective function rho, which outputs the cylinder here, has this property that 0y and 1y go to the same point because sine and cosine of 0 and 2 pi are the same, right? And so this function rho kind of like makes this gluing happen. Okay. So we don't always need to actually write down what the function is. That's part of the great thing about topology is we can not have to write down what the function is. But I wanted to show you that we could, okay? We could if we needed to. So now that we sort of believe that we can, we're not going to worry about the function anymore. We're just going to sort of say, okay, we sort of know what rho does visually, and in particular, rho implements the gluing as stated in this equivalence relation. All right, so now let's talk about what are the open sets in the cylinder. What are the open sets? So to find out if a set is open, you have to look at its pre-image. So I imagine taking rho and going from the unit square to the cylinder. If I were to take an open sort of circle, like in the subspace topology in R3 on this cylinder, and I look at its pre-image in the unit square, it looks sort of roughly about the same. Okay, it's imagine you just unfolded a piece of paper. And so the open sets in the unit square, the ones in the interior of the unit square, just look like open balls. And that would come from an open ball on the cylinder here. Okay. Rho is injective there. It's 1-to-1. So it basically just sort of takes that open set and like wraps it around the cylinder. Okay, so that's one type of open set in the cylinder. Another type of open set is what you get when you go, you look at points that are on the edges of the unit square, the edges that have been glued. So if I look at edges that have been glued, then this open set right here corresponds to the open set I get by taking part of an open ball on the right side and then part of an open ball on the left side. And notice that like these points need to match, okay, because the inverse image of this, they'll be coming from like this point and this point have to be equal, and this point and this point have to be equal because they're coming from corresponding points over here. And so you can see that basically what's happening is as I'm gluing to get an open set in the cylinder, it has to come from two like sort of partial open balls in the subspace topology on the unit square that had to end up getting like glued together just right. Okay. What about if I didn't draw it on here, but what if I did an open set kind of like another type of open set in the subspace topology is a set like that down there? That would correspond to like an open set right there. Okay. So I claim that the topology that we're looking at on the cylinder here is the subspace topology. So the quotient topology that I obtained by taking the unit square and gluing the vertical edges together is the same as the topology that I would get by taking the cylinder and taking the subspace topology in R3. All right. And then finally, the notation that we'll often use for this sort of gluing is that I'll draw my unit square and I'll shade it just to be clear that it's the same one we've been looking at. And then I'll draw some kind of like arrow or labeling or something. So I'll maybe put arrows like this. And that shows that I want to glue those two vertical sides together and in the same orientation, like the top point goes to the top point. I'm not like flipping one over. Okay. All right. And so a topologist would say, here is a picture of a cylinder. That is a cylinder. Okay. It may not look like a cylinder to you, but we know that that is a representation of a cylinder because after we finish gluing the vertical edges together, it is equivalent to a cylinder. It's homeomorphic to a cylinder. All right. Thank you for listening.